Okay, so we've looked at the bonding in ethane and bond rotation. Now we're going to add two more carbons and look at the bond rotation in butane. Now butane here has these four carbons, and we're going to specifically look at this carbon-carbon bond here because we want to do a Newman projection, and we want to line up this carbon and this carbon. So when we're going to be looking at ethane and bond rotation, we're going to be looking like this. So we're going to be looking down straight through this carbon-carbon bond. A little difficult to see with this model, but looking at this way, so when we rotate, we'll be rotating it like this. All right. As you see this rotation, can you see how we are in the staggered with the 60-degree dihedral angles right here. In this rotation, it's staggered, and we can rotate it 60 degrees, and now we're in the eclipsed rotation, and we can go back to staggered. We could keep going around, and so that's what we're going to do. But we want to pay attention to the fact that we've got a methyl down here and also a methyl up here. Note these two methyls are opposite of each other. One's way up here, one's down here. We're in the staggered conformation with the methyls on opposite side at a 180-degree dihedral angle, and we call this the anti-conformation. So now we're going to start drawing Newman projections of butane here, looking down that C2C3 bond, and we're going to have the methyls, as you can see here, in the anti-configuration. Note the way this is drawn here. We've got the front methyl coming down. The back methyl here is going up. Front methyl is coming down. And that's what we have here. Okay, so this is the anti-configuration. As we rotate 60 degrees, we come into this eclipsed conformation here. If we rotate another 60 degrees, this methyl gets up here, and we're in what we call the gauche conformation. Another 60-degree rotation, and the two methyl groups are eclipsing each other, and we call this is another eclipse conformation, but note here we have the two methyl groups eclipsing each other, whereas here it was a methyl and a hydrogen eclipsing each other. Another 60-degree rotation, the top methyls to the right, we're back to the gauche. And another 60-degree rotation, we're eclipsing again, and if we did one more time, we'd be back to anti. So on our models, and I highly recommend you get some models so you can do this, just line it up, and here we are anti, rotate 60 degrees, and we're in eclipsed. Another 60 degrees, we're in gauche. 60 more degrees. Now note that the two methyls are now eclipsing each other. 60 degrees more, we're back into the gauche conformation. 60 more degrees, eclipsing again. 60 more degrees, back to anti. So that's what we've done in here. Now the question is, are all the eclipse conformations the same energy? Or some more stable than the others? Are the staggered all the same energy? All right. Well, when we look at our barriers to rotation, we've already talked about the torsional strain due to the energy of the hyperconjugation in the eclipsing conformation that makes staggered lower in energy, makes staggered more stable. All right, but we also need to look at steric hindrance, something else comes with torsional strain. The thing is, when we look at the two methyl groups eclipsing each other, when we look at this conformation right here with the two methyl groups eclipsing each other, what we find is that these two methyl groups can get pretty darn close to each other. Here we are eclipsing, and if I turn this just right, we can see those two hydrogens are pretty darn close to each other. Now, we do have a little bit of a problem here, and that's with these molecular models that you would buy. is that when we look at how atoms are really bonded together, note this part right here, this carbon is actually the nucleus of the carbon atom. This ball right here is the nucleus of the hydrogen. We are not actually drawing how the molecules really look, how the atoms really look, because if we did that, what we would see is that if we had a carbon atom, this carbon atom bonded to this carbon atom would actually kind of look like this. They're just circles that overlap each other, and the three hydrogens are smaller circles overlapping, and one back here. And what we find then is when we actually consider that they are not just little balls at the end of sticks here, that when they're actually spheres bonded together, what we find is these two kind of run into each other. The electron density, the electrons of this hydrogen might run into the electrons of this hydrogen over here. And of course, they're both negatively charged. All electrons are negatively charged. And so the electron clouds, the electron density smacking into the other electron density, two like charges repel each other. So that offers some hindrance. We call that steric hindrance when, due to just bulkiness, due to electron clouds bumping into electron clouds, they don't want to work. Now, if we had the proper models, which are quite expensive, we would see that if the two hydrogens were in this orientation, you actually could not rotate these past each other, you could not actually get into the full eclipsed conformation that we have right here. See how it's totally eclipsed? But if we rotate one like this, we could see this will work. And so actually when these two go by each other, when they're rotating, it does something like this. Whereas this one rotates, they also, as this bond rotates, moving this carbon up, we find that these bonds kind of rotate too to let the other one pass. So you've got this steric hindrance and the hyperconjugation. Hyperconjugation means that eclipse is just higher in energy to begin with, and steric hindrance especially affects the energy of the eclipse conformation, with things kind of getting too close together, kind of running into each other. And so now when we do the potential energy versus reaction versus rotation diagram, what we see is that the anti-configuration is lowest in energy. The eclipsed is higher in energy. The gauche conformation is a little bit higher in energy than the anti. Not much, just about 2.8 kilojoules per mole, but it's a little higher in energy. The fully eclipsed, with both methyls eclipsing each other, is our highest energy on this curve. And then we go back down to gauche, which is just a little higher than anti, back up to this eclipse here, which is not as high as the methyls eclipsing each other due to no steric hindrance here, and then back down to the anti. And so this curve looks like this, and if you kept going, we'd repeat that pattern. All right. However, even though this fully eclipsed, the two methyl groups eclipsing each other, has a higher energy gap, this 19 kilojoules per mole energy gap, it is still not enough to stop the rotation along that bond in butane. That molecule is still just rotating all over the place. All right. All right, so closer look at van der Waals forces. We'll just go through this. Note that the electron clouds of one group are actually attracted to the nuclei, the nucleus of another group. So as these two come closer together, there's actually a little bit of an attraction between these two, as the electrons on this hydrogen here are attracted to the nucleus of this hydrogen over here. So at distance, there's a little bit of attraction, but then they get too close together, and the two electron clouds start repelling each other. All right. Note that this attraction is maximum at the sum of the van der Waals radii of the two groups. That's when you get most attraction, but then they get too close and you get repulsion. This electron-electron repulsion is our steric hindrance. The larger the group is, the more steric hindrance it's going to have. All right, now let's look at cyclohexane, or cycloalkanes, and then we're going to add another layer to this. We're going to add ring strain. All right, it turns out that cyclohexane is one of our most stable rings. Another way of saying it is it has the lowest heat of combustion per CH2 group, gives off the least amount of heat energy, means it had the lowest potential energy to begin with. All right, so cyclohexane is a very stable ring. And let's start with smaller rings. Let's start with something like a cyclopropane. Note that cyclopropane is, we draw it, it's a triangle, right? And here's the deal. The angle on a triangle is 60 degrees. But this is still a carbon bonded to two other carbons and two hydrogens. So it wants to be tetrahedral. It is still sp3 hybridized, meaning it wants to be a tetrahedral molecule. But due to the fact that we've made a ring, we're forcing it to be closer to 60 degrees instead of 109.5 degree angles. So we call that angle strain. Whenever the angles of a cyclic ring are not 109.5 because the ring won't allow it, we call that angle strain. All right. So what we'll also see with cyclopropane is that in addition to this angle strain, that if you were build the molecule, and if you don't, that's fine because it really wrecks your molecules. I can't even build one with this because it would just bend everything up and these things would break. What we would find is all of the hydrogens are actually eclipsing each other also. So all hydrogens are eclipsing each other, which we know is higher energy. So that's our torsional strain. We also have this angle strain here, and torsional strain plus angle strain gives us ring strain. And cyclopropane has a lot of ring strain. The bonds are actually, if you look at it, the bonds are actually kind of bent a little bit in cyclopropane. So our torsional strain plus angle strain equals our ring strain. Cyclopropane, lots of ring strain. Cyclobutane. Now I'll try to make it with my molecule here, with my models. And we'll put a bond here between these carbons. And note, it's not happy. Here's my cyclobutane. Note you can see some bending in these bonds because instead of 109.5, I'm forcing these angles to be 90 degrees, which they don't want to be. So we've got angle strain because we have 90 degree angles instead of 109.5. And note that when we look at it, all of the hydrogens are pretty much eclipsing each other. See how this one back here is eclipsed by the one up here. This one down here eclipsed by this one, and so forth. No matter how we turn it, we always get some eclipsing. Now there's a little bit, probably a little bit of pucker to these, but even my models don't want to pucker up that much. A little bit of bending in here. But cyclobutane has a lot of ring strain also, due to lots of torsional strain, due to the eclipsing hydrogens, and lots of angle strain due to 90 degrees instead of 109.5. All right. Now, when we go to cyclopentane, what we find is if we make it like this, if we make it like a flat pentagon, we would say, okay, the angles aren't that good. Everything's eclipsing. Look at those guys are eclipsing there. These guys are eclipsing. Here's the back one eclipsed by the front on both sides. Everything's eclipsing. So it looks like it's got a lot of angle strain and torsional strain. Not as much angle strain, but it turns out that it puckers. And even on your models, you can get these to pucker a little bit. So it's not totally flat. See, it's got this little bit, as I turn it on its side, it's got this little bit of pucker to it where If I try to find a flat side here, like these are kind of flat here, we can see this one's down. There's just, you can't, yeah, it doesn't sit flat on the page. There's no way to make it flat on the page. It's kind of puckered up. If you move the camera angle, you can see, okay, yeah, it's all puckered up and everything like that. All right. So, what that does is two things. One, it alleviates some of the angle strain such that we're at 108 degree angles instead of 109.5, and so that's pretty good. But note, look what happens here. When I look at these two carbons, the dihedral angle, look at that. We've got this one here, and it's in between the two down here. This is pretty much staggered. This has pretty much got a staggered configuration here. And we go to the next two dihedral angles, next dihedral angle here, or Newman projection here. Look, we got some, this is staggered also. So, not the greatest. This angle here doesn't look too good. But we don't have as much ring strain or torsional strain because of that. Now, the party won't last for long because if we look at this, this is almost eclipsed. I mean, look at this guy here. It's not directly behind this one up here, but it's pretty close. And this one isn't directly behind this one, but it's pretty close. So this is awful darn close to eclipsed here. The next one over, oh my goodness, yeah, that's eclipsed. So we got that. That's eclipsed. That's bad. This is close to eclipsed, but not quite. But then the next two are staggered. This one is staggered. Oh yeah, nice and staggered here. And this one also very nice and staggered. So we're not totally eclipsing. There's a little bit of eclipsing going on, but not too much. What this means then is cyclopentane does not have that much angle strain. It doesn't have that much torsional strain, but it does have some. Not much angle strain, plus not a whole lot of torsional strain means not a whole lot of ring strain. There is some ring strain here, but it's not a lot of ring strain, which means cyclopentanes are fairly stable. They're fairly stable molecules, and they do exist just fine. All right, starting the next video, we'll look at all the fun we can have with cyclohexane.